In this video, I'm going to calculate the fall impact that a lead climber takes when he falls. On the right here, I've drawn up our situation. The really two important numbers here are the height that the climber is above his last piece of gear and the length L of rope out between the harnesses of the climber and the belayer. So thinking about this in terms of energy, at the height of his fall, he's going to have potential energy. That's going to become kinetic energy when he falls. And then he's actually going to do work on the rope, or the rope is going to absorb his energy. And here kinetic energy is an intermediate form, so we'll cut it out. And next, what form will this potential energy take? Well, it will be mgh, but he's going to be falling not at distance h, but a distance of 2h, because there's still going to be a length h of rope out when he gets to here, and so he'll fall down to about here. So that will become 2 mgh, and that will be equal to the work. And in this expression, the work takes the integral form because the force is not going to be constant as he goes down. So if it's not constant, then we have to wonder, well, what will it be? And if you do some research and you look online, at any given rope there's some characteristics supplied by the manufacturer, like the dynamic force, the dynamic elongation, the static elongation. With that data, you can kind of plot something, and it will look roughly like this. It will be something like a straight line, and this will be percent elongation, not just rope stretch. So that's actually very similar to strain in the engineering world. And with that data, let's say this is slope K. Yeah, and now we're going to switch from X would be the rope stretch, to strain. And strain is equal to stretch divided by the total length of the rope. So that means that dx is equal to LD. And then coming back here, the integral, our f here, is actually Ke, and then dx becomes LD. And this is going to go from a strain of 0 to our final strain, 2 mgh. Let's move the constants to the left-hand side, KL. And then with the constants over here, this integral becomes pretty easy to evaluate. It will actually turn out to be just this. And then we can solve for our final strain. 2, yes, square root of that. And then here, based on the characteristics of our rope, we know that the force is equal to some constant, the slope here, K, times the strain. That means that the final force is equal to K times the final strain. And this is, since the force is increasing with more strain, we know this is the maximum force. So then our final force is, take the 2 out, mgh(k) divided by L. This tells us the important things in determining the maximum fall impact. The mass of the climber is important. This is a constant. The stiffness of the rope is important. That's why we use a dynamic rope. And what's most important is this h over L thing. That's actually fall factor.